All right, we're talking about the area between two curves today, and you already have the tools with integration to be able to find the area under a curve in between the curve and the x-axis, right? So if I gave you this function here, f of x, and I said, what is the area of the curve, or area under the curve in between f of x and the x-axis, you could tell me that this yellow area right here was the definite integral from a to b of f of x, right? That's what the definite integral means. It means finding the area under the curve. And then if I gave you this g of x, you could also tell me that this area under g of x to the x-axis is the definite integral from a to b of g of x. So if you are able to find those two areas, how do you think you could use that to find the area under the curve, or in between two curves, excuse me? Well, if you know the big area, and you know this part of the area, don't you think that if you take the whole and you subtract a part, that you get the other part, right? If I take the entire thing and I subtract one part of it, I get the other part, which makes sense, right? So when I'm trying to find the area under the curve, or the area in between two curves, basically what I do, especially for functions of x, is I take the top curve minus the bottom curve, and I take the integral. And what we remember from the rules of integration is that if I take the definite integral from a to b of f of x, which is the area under the curve of f of x, and I subtract the definite integral from a to b of g of x, excuse me, I really should have that dx on there, then that's the same as what you see right here. That's the same as if I combine them. Remember, because integrals, just like derivatives, can be combined. Like I can split them apart, put them back together if I like. So what I can say is I could find the area between two curves. I could find, the area of the one and subtract the area of other, or I could subtract the two from each other and then take the definite integral. And either one of those is going to give me the same answer. So we're going to go ahead and find the area under the curve. Now, one thing I want you to pay attention to is the areas cannot be negative because we're talking about, like a certain amount of space. We're finding an actual area here, not a signed area where we're talking about like negative and positive accumulation. We're talking about, the space in between these two curves. Just like on a plain old number line, if I, let's see if I can find some space up here on my thing. If I had a number line and I asked you, here is -1 and -4, and I said, what's the space in between these two numbers, right? How much space is in between -2 and -4? You would say it's 3, right? There's 3 in between there, right? We wouldn't say -3 necessarily. We're just talking about how much space does it take up, right? It takes up 3 spaces. It's the same thing for these. So we're talking about the actual space that this takes up in between the two curves. So this is always going to be a positive value, and I'll show you in a little bit. Even if the curves are below the x-axis, this still works. Okay? So basically what we're going to do is we're going to find the area in between two curves by taking the top curve minus the bottom curve and then do the definite integral. So this first one, we have the area in between y equals x squared plus 2 and y equals x. So I'm just going to go ahead and label this f of x. And I'm going to label this one g of x so that I just have, like, I can refer to them a little bit better. So we know that the area in between them is the definite integral from a to b of f of x dx minus the definite integral from a to b of g of x dx. Okay, so what we're saying that we want the area in between the curve from 0 to 1. So our a is 0, b is 1. So we're going to go ahead and do the definite integral. And remember, we're just going to combine these. So we're going to do the definite integral from 0 to 1 of f of x minus g of x dx. So we go ahead and just do a little bit of simplification here. What does this actually look like when we subtract these? So we go 0 to 1 of x squared plus 2 minus x dx. And then we integrate. Well, and since this is individual terms, it's actually really easy to integrate. So we have x to the third over 3 plus 2x minus 1. We'll do it this way. Minus x squared over 2, evaluated from 0 to 1. So then we evaluate this from 0 to 1. When we put 1 in here, we get 1/3 plus 2 minus 1/2. And then when we put 0 in there, we get 0 plus 0 plus 0. So, in the end, we have 2/6 yeah, I don't think we need this in 6. We have, oh yeah, we do need this in 6. 2/6 plus 12/6 minus 3/6, which gives us 11/6. So the area in between these two curves is 11/6. Now, what you might be thinking is, oh, that's all fine and dandy because they're above the x-axis, so that makes sense because, you know, this is all a positive area to begin with. So I want you to really, really think about this and think about what would happen if I shifted these functions down, right? Would the space in between those two functions actually change? Just like if I think about my number line, if I shift this purple piece, if I shift the purple piece to the left or to the right, does the amount of space that that purple piece takes up, does it actually change? It doesn't, right? It doesn't matter if this goes from 4 to -1 or 0 to 3 or 100 to 103. That purple piece stays the exact same size if I'm shifting it to negative or positive numbers, right? So it's the same thing for these curves. Even if I took this green area and I shifted it so part of it was below the x-axis, the size of that area stays the same. And you just need to trust me on this. There are some kind of exhaustive proofs of this, and I've put a link to them on our calendar if you'd like to. It's like the last video that I linked that show some, I guess that one's not really a proof, but it's a little bit more of an explanation of how it works mathematically. But remember, the area is going to stay the same. So still, if we take f of x minus g of x, it is still going to give us the same area. And the other thing that I want you to think about is that if you think to our Riemann sums, and you think of the fact that a Riemann sum is basically just drawing rectangles to find the area under a curve, right? Well, with our definite integrals, or with our area between the curves, we are kind of doing the same thing, if you think about it. We have these rectangles, right? We could draw rectangles to figure this out, and we're making these rectangles infinitely small, which is what, you know, our integral basically does. But we have all these little rectangles, and the width of this rectangle is the change in x, it's dx. And then the height of the rectangle would be whatever f of x is minus whatever g of x is, right? Because the height of this rectangle down to the x-axis is f of x. And then I have to subtract whatever g of x is, and that's the height of my rectangle. And so, if you look at our formula for the area in between a curve, what we found is that we're trying to find the height, or the area of these little tiny rectangles. Look, here's the width of the rectangle. Here is the height of the rectangle. Isn't that crazy? So here we are finding the height, or the area of these rectangles. We have width times height. And so this is kind of important to think about because here in the next video we're going to see one where it's actually turned on its side a little bit, and we're actually going, we're taking it in terms of y. We're taking functions in terms of y. So when you're looking at these, I want you to think of these little tiny rectangles. In fact, I even thought, when I first learned these, I thought of like a scanner, like a scan gun that's like going like beep, 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 right? So it's like touching the top, and we've got a line that goes down to the bottom, so that's how I know what the bounds are. So hopefully that wasn't overly confusing. I think it'll become clearer as we look at the next video.